Right, hello. This video, I hope is that you have a better understanding of probability distributions. So we start off with that a probability distributions is about a random variable, and we can call it X or Y, any capital letter we use. Just need to be consistent. Before we go any further, you need to remember that we have two types of variables. We have discrete, which it can take on any integer values. For example, the number of heads when flipping two coins. So that's definitely a discrete variable. Continuous, it can take on any real values. For example, heights of 1,016-year-old boys. Now, when we are focusing on these two examples to compare, then over here, the number of possible outcomes of getting the number of heads would be 3. So you can have 0 heads, 1 head, or 2 heads. Now this is the visual, which we can use a line graph or a bar graph for it. Let's take a look at this table. This table is called a probability distribution table. And so this is how we use a different representation to list out all the probabilities. So since the random variable x is about the number of heads, so we are going to use a smaller lowercase x to represent all the possible values it can take on. So 0, 1, 2. So the probability of x is equal to 0 would be 1/4. The probability of x take on the value of 1 is half. Lastly, we have a letter k. And how do we figure it out? Now, of course, this is a simple example. You know it should be a quarter. But if it is a much bigger example with more possible values that x can take on, then you will have a much longer table. But no matter what, we know that all these probabilities will add up to 1. And because of this, we can use it to work out what k is. So in this case, k must be 1. Take away a quarter, take away a half. So we will have a quarter. Now we can go back to the bar graph or the line graph. Now that we know, we can represent a bar of a quarter for 0, and then up to half for 1 head, and here for 2 heads. Or we can opt to use a bar graph like this. That's 0 heads, 1 head, 2 heads. In terms of using the GDC, we can use the listing spreadsheet and enter it. But we need two columns. The first one, number of heads. So we will have 0, 1, 2. So that's our x. And then the probability of the random variable take on these values accordingly. It would be a quarter, half, and a quarter. From here is pretty much like what you have learned in statistics. We can use one variable stats to work out the mean and then the standard deviation of it. But we need one variable stats because it is about the number of heads. Over here, if we go back to the continuous random variable, we would have a classic bell-shaped curve. And this is called, the example I gave here is a bell-shaped curve. Of course, it can skew either way. It can skew like this, or you can skew it like that. It all depends on what parameters you are working with. But for this particular one, it is continuous, bell-shaped, and symmetric about the mean. What you should notice that is the area under the graph must equal to 1. If I do the same thing over here, as you can see, it's pretty much showing the same shape, but we can't put a curve there because here we're dealing with discrete variables. So it can only exist as bars or lines. Over here, you have all continuous values forming a curve. But no matter what, the area under here is 1, and the sum of these bars must also equal to 1, because all probabilities add up together equal to 1. Before I move on, one last thing to mention is, if we go back to here when you use your GDC, you need to know that this is your expected value, which we use E bracket X to represent. This is equal to the mean. Now, when we have questions about whether a game is fair or not, you need to remember that the expected value has to be equal to 0 before we can call any games a fair game. And this would be useful when we do questions which ask you, well, how do you determine whether this game is fair or not? Then you need to make use of this property. Now let's go into discrete variable and continuous random variable. So I'm writing RV, so random variable. The two that we have done in lesson is binomial distribution and normal distribution. So some of the properties about the distribution that you need to remember. Binomial distribution is about you're dealing with fixed number of trials, and we call it n, fixed number. Only two possible outcomes, so either success or failure. And the parameter that we use for it is p. Failure has to be 1 minus p. All the trials are independent. Basically, it means the probability will not change for each trial, so it will stay the same. If it changes, then it will not follow a binomial distribution. And P for success, 1 minus P for failure. With the binomial distribution, we will also look at the expected value, which I just mentioned before is about the mean. And it is quite easy to calculate. It is n, the number of trials, times the probability of success. The variance is the number of trials times the probability of success times the probability of failure. Standard deviation is the square root of the variance. So this is sigma squared, and then you will have sigma, which is the square root of n times p times 1 minus p. And the notation that we write to indicate that we are dealing with a binomial distribution goes like this. We say the random variable x follows a binomial distribution. Now you need to tell clearly what the parameters are. So we use this. We say we write down the number of trials and then the probability of success. As you can see, if we are given something like this, we can quickly work out what the expected value is. We can work out what the variance is, and then use it to work out the standard deviation. The visual representation of a binomial distribution can look like this. So, just like the one about flipping 2 coins and getting the number of heads. And the discrete representation, so you have bars. And then the number of bars, of course, is showing all the possible outcomes. So over here, you must have 0, 1, 2, 3, and this represents 4. That's 5. Now, we don't know what the probability of success is, but we can already say something like this follows a binomial distribution with 5. And we can maybe make up a probability of success, saying, oh, it is 0.2, like that. Now, comparing it with the normal distribution. The normal distribution is a distribution dealing with a continuous random variable. And it's usually large, so you're dealing with very large numbers. And it arises in nature a lot. The mean is, and the variance would usually be given in the question. But say if you don't, you can calculate the mean and the standard deviation from the GDC, and you can use those for your mean and variance and standard deviation. It doesn't happen a lot, so I wouldn't worry too much about it. The notation that we use to show that a random variable follows a normal distribution is bracket, and then we will have mean and sigma square. So you'll be very careful, particularly about this. So I'm going to write it, sigma square. What you need to be aware of is sometimes questions give you standard deviation, but when you write this, you need to write the standard deviation squared. Sometimes they give you the variance. And when you do the calculation, you need to remember to square root it to get the standard deviation. For example, you might be given something that the mean is 99, and then you have 2 squared. Okay, then you know the standard deviation is 2. The variance is 4. Or it can be given to you this way. 4. Now, that means you need to square root it to get the standard deviation. This bell-shaped curve, symmetrical about the mean. The mean given to you, for example, using my example, it would be 99. So 99 here. We need to make use of the standard deviation too. Like this. So how does it spread out? Spread out like this. 99 minus 2, so 97 here. 99 plus 2, 101. So this is plus or minus 1 standard deviation away from the mean. Of course, then we have 2 standard deviation away, then 3 standard deviation away. Now we're interested in the area under the graph. The area under the whole graph is equal to 1. Or if you can also look at it, the area under the whole graph is equal to 100%. Because it is symmetric about the mean, therefore, if we are just doing half of it, this must be 0.5. And over here, the leftover must be 0.5. We're going to look into binomial distribution and to have a specific example to go over how we use the GDC. Now I'm going to use my made-up sample on the previous page, saying that the number of trials is 0.5 and the probability of success is 0.2. Since binomial distribution is about discrete random variable, then we can have it equal to an exact value. So we can say, oh, what is the probability of x equals exactly 2? Now with that, we need to use binomial PDF. So this would give us the probability at an exact value. So go to GDC. You need a calculator. Now to break up the binomial PDF function, you need to go to Menu, Statistics, Distributions, and then here, look, Binomial PDF. Now click on that one, and you will have 5, 0.2. But to sidetrack a bit, let's just try not entering the x values. You will get the probabilities of every single possible values that x can take on. So this is when it is exactly equal to 0, exactly equal to 1, etc. But in order to see what's at the end, you need to use the cursor button to go all the way to the right. But we can see already when x is equal to 2, this is, it should be 0.2 over 8. But let's say, well, we just go back to the menu, go to distribution, PDF. We enter exactly what we need. I could put 2 here. Then I get 0.2048. So we can write that over here. We enter 5, 0.2, and then it is exactly 2, equal to 0.2. This should be what it should show on your GDC app. Say we're interested in the interval. So we are interested in the probability of x in between 0 and 2 inclusive. But this is accumulative. If it's 0 and 2 inclusive, we are interested in adding up the probability of these 3. So we now need binomial CDF. The C means cumulative from the left-hand side. We need to say, oh, it's 5 for n, 0.2 for probability of success, starting from 0 ends at 2. This time, instead of selecting PDF, you need to go one more step down, and you need to get binomial CDF. It's 0.942. How about we are only interested in P of x being less than or equal to 3. So if you go to the graph, we need everything less than or equal to 3. these four. Your calculator has this function. If you move your cursor up, it highlights the answer, and if you go one further up, it highlights the command. And you can copy it by pressing enter, and you can change the values you like. So in this case, I need to change it to 3 because it's 0 to 3 inclusive. And it gives me 0.993. So when I answer this question, I would write down what I enter into the calculator. So I enter binomial CDF 5 0.203 and equal to 0.993 to 3 significant figure. The last one is probability of x greater than 3. So if we go up here, greater than 3, meaning we can't include 3, we only are interested in 4, x equals 4, and x equals to 5. Now one way of doing it is, of course, you can tweak this command a bit. So 4, 5, like this. And then you work out in here. I'm going to copy that one, change it to 4. Zero 0.00672. But of course, if you look at this, they add up to, these two probabilities will add up to 1. In other words, this can be looked at as 1 minus the probability of x is less than or equal to 3. And you can do 1 minus 0.993 to get the answer here. But of course, you will lose, if you do it this way for this particular question, you will lose some of the accuracies at the end. So to avoid that, you can use your calculator, say 1 minus this answer. And then it will give you that. So try not to use the one that you have rounded down, and use the calculator whenever you can. It's not necessary though. As long as you know how to use the command and use the lower bound and the upper bound correct, you get the job done. But it is good to understand this means 1 tick away for x is less than or equal to 3. Next, let's take a look at the normal distribution. The normal distribution, we will have the random variable x follows the normal distribution with the parameters mean and sigma square, variance. I'm going to make use of this example. I actually missed out the end here, so I'm gonna 30 and 25. So I'm going to change it to normal distribution, 30 and 25. Now 25 is the variance, so I can actually change it to a 5 square to know that I'm dealing with the standard deviation is 5. So I can write 5 square here. When you do normal distribution questions, it is very important to sketch. So always sketch a bell-shaped curve. It doesn't have to look very neat and tidy, but the more you practice, it gets better. Now, if you have this distribution, you can enter the details on your normal bell-shaped curve. So we know that the mean is 30. The standard deviation is 5. So take one standard deviation away, we get 25. If we add one standard deviation, we will have 35. And you can keep going. This is 2 standard deviation away. This is 3 standard deviation away. If we know what variables that we are dealing with, we can also, of course, label here to make it very clear. Normal distribution is about continuous variable. You will never ever need to deal with that. For example, over here, comparing with binomial distribution, we can have exact value probability of x is equal to 2. It will never happen here with normal distribution. The probability, for example, if x is exactly equal to 25, is 0, because you have a continuous variable and it's considered not possible for it to equal to an exact value. You consider the probability is equal to 0. You always look at the normal distribution in the accumulative sense. Let's take a look at the first one. We're interested in finding out what is the probability that x is less than 15. So we can go to the calculator. Now this time, instead of selecting binomial, we use normal CDF. Now, how do we enter the lower bound and the upper bound? We want it to be less than 15. Now, where is our 15? We know that the mean is 30, and then 15 is somewhere over here. And so what we're interested in is just this area. So what's the probability of this highlighted area? The lower bound, in order to enter the lower bound into the GDC, it has to be, you understand that it is all the way from the left, which is because of the asymptotic property of the normal distribution curve. We know that this goes on forever, but never touches 0. Meaning you can imagine this, when going to the left, it goes on forever. So it can go really, really negative. That's why when by default, your calculator will give you -9 times 10 to the power of 999. This will give you an extremely small value. You can also opt to enter that yourself and say that, we can do 999. So just enter a lot of nines. upper bound is up to 15. The mean is 30. The standard deviation is 5. So make sure you use standard deviation and not the variance. Where did it go? Negative. I forgot to put the negative, that's why. 15, 30. Now that's better. So in terms of showing your work, it is perfectly okay to write down what you enter into your calculator. And this is 15, 35. Then we get 0.0135. 3SF. Well, how about this one? Probability of x greater than 45. We know that this is 30 here, 45 somewhere here. We want this bit. Now, I deliberately picked 45 because I want you to see this is 15, 45 is over here. They are symmetrical. Okay, so if I work it out on the calculator, it should give me this value. Let's see. Now this time, the lower bound changed to 45, the upper bound changed to a very, very positive, big positive number. But the mean and standard deviation is, as you can see, they are the same. That's because they are symmetrical. So if I write the details on the graph, we should have 30 here, 45. This is the area of interest. Normal CF, we will have 45, really, really positive, big number for the upper bound, 35. We will get 0.00135 again. Next, let's say we're interested in what is the probability of the random variable x being in between 18 and 37. So better have a sketch, write down where the mean is and roughly where 18 and 37 would be. So what about there? It doesn't have to be exact, as it is just a sketch. You have here, there. So I want in between, meaning I am interested in this area under the curve. So you shade it. Now this time, because we play with the upper and lower bound, we can see that then 18 must be our lower bound, and then 37 must be the upper bound. So let's copy this one and change it. I can change this to 18. then we get 0.911. The last thing I want to look at with you is this 2. This time, we were told that the probability of x being less than a certain value is 0.3. Now, because we know the property of the normal distribution curve, we know that this side is half of 1, so it's 0.5. If we are told that the area of x being less than a certain value is 0.3, meaning we are only dealing with probably that much of the area, and this would be the value of a. So x being less than this is 0.3. We should add that onto our drawing. So we have 30 here, a here, and this is 0.3. Now, since we are already given the probability and we are asked to find out where does that happen, what a is, we need to use inverse normal. So we need to reverse the process. On your GDC, you go to statistics, distribution. This time select inverse normal. It's asking you, oh, what's the area? Oh, 0.3. Begin with a mean of 30, standard deviation of 5. So it gives you 27.37799, meaning A is to 3 significant figure is 27.4. So we can write down this inverse norm 0.3, 30. How about this one? This time we say, oh, what's the probability? Oh no, the probability of x is greater than a certain value is 0.3. Now, where do we put the a? We know that 30 is here. If we know that it is 0.3 and is greater than value, a cannot be here. If a is here, plus this 0.5 is already exceed 0.3. So a must be somewhere here, bigger than 30, to have this probability of 0.3. However, your calculator won't be able to do that. It reads the area from the left. So instead of thinking it that, oh, it is 0.3, you need to think the complement of it. So let's write down some values. This is 30. A is over here, 0.3. We can't use this because it's on the right hand end. So we're going to change it to say this. And of course, this blue area has the probability of 0.7. So what could A be? We need to enter inverse norm 0.7, 35 to find out. So I'm going to say that. So 0.3 will be 0.7. So A is equal to 32 6. So now this side by side, you can tell clearly the difference between binomial distribution and normal distribution. Although most of the time, the question would indicate it already what sort of distribution you're dealing with, it is good to know the difference between